Yes, so just to make sure, so it should be an hour or less or
Yeah, it's an hour. Yeah, it's
okay.
an hour. All right, so let's start our today seminar. Actually, I'm not sure whether it will be last seminar. We will have one more. Okay, so let's start today seminar, and we are happy to have Murad Alim, currently from the Maxwell Institute for Mathematical Sciences and Heriot-Watt University, everything in Edinburgh. And the title is on his first slide, From Gromov-Witten to Donaldson-Thomas Invariants via Resurgence. Murad, please.
Okay. Thanks a lot for having me. So it's a pleasure. I hope we meet in person at some point. Yes, so what I'm going to talk about is some work of the last 2 to 3 years. Some of it by myself, some of it with wonderful collaborators. So these are Lotte Hollands, she's also here at Heriot-Watt and Maxwell Center, and Arpan Saha, who's now back in Hamburg, and Jörg Teschner from Hamburg, and Iván Tulli, who's now in Sheffield. And yes, so the plan of my talk, so I'm going to spend a lot of time giving you motivation introduction. So I'll just reconfirm that the M in the M seminar and M center stands for mirror symmetry, but nevertheless, maybe just give some recap about how I think about mirror symmetry. And then about topological strings. So also Lino asked me to suppress physics. So whenever possible, and whenever I know the terms, I'll try to say them in both languages, but also I will not completely avoid physics just in order to give some connections between things. And then I'll talk about analytic structure behind Gromov-Witten theory, so as accessed by a resurgence, then mention some early results and then also some work in progress on topological string theory and S-duality. Okay, so let's start with a motivation. So I'm a mathematical physicist, so I'm between math and physics. And wonderful things happen between math and physics. So the particular type of interaction that I'm interested in is the geometry of quantum field theory and string theories. And one particular aspect of this is the study of moduli spaces. So it was realized that from the physics perspective, for instance, if you don't think about isolated physical theories, but rather try to think about theories as coming in families, where the families are parameterized by the couplings of the theory, the masses, and whatever free parameters that you have, that sometimes there is a clean translation into where the parameter spaces of the physical theory admit an interpretation in terms of mathematical moduli spaces. So an early example of this is the study of Zybeck and Witten, where they studied an SU2 gauge theory with supersymmetry. But it turned out that when this theory is studied all over its parameter space, it's really just corresponds to one particular boundary point in this parameter space corresponds to the original theory. But generically, the theory can be very different. And what we also understood is that there are these, so the dotted lines here, and generically in these moduli spaces, there are walls, so now known as walls of marginal stability, where some discrete data of the theory changes. So there are two things. So there is some continuous aspect of changes of not the theory itself, but some data associated to the theory, such as couplings, masses, and so on. So this is in the realm of mathematics, will be captured by flat connections. So we'll see this in a bit. But then there is also some discrete changes. And both of these aspects will play an important role in this talk. So let me continue with the motivation. So this let me see the translation into a well-known mathematical moduli problem where on the mathematical side there was hot structure of an elliptic curve that is varying. So this gave the continuous variation, a flat connection, and a system of differential equations. So this led in the physics to exact results. On the other hand, it's also, from the mathematical point of view, it's very interesting and very inspiring to have the physics in mind, because oftentimes natural ways of organizing, especially in the field of enumerative geometry, natural ways of organizing mathematical invariants correspond to some physical ways of organizing things. So in particular in my talk, I'll talk about Gromov-Witten invariants. So there is a way of organizing Gromov-Witten invariants of particular spaces. So in particular, in my talk, it's going to be Calabi-Yau threefolds, where it's formal organization by the genus of the underlying Riemann surface, and there's a physics way of organizing this corresponds to what's called a perturbative formulation. So there's just a summation over formal parameter genus by genus. But then there's also other ways of organizing mathematical invariants attached to the same
So is it problem with my Zoom or with his?
It seems his connection dropped, apparently.
Okay. I see, because I thought that it might be my Zoom.
He
Okay.
probably lost connection. Something happened.
Yeah, I don't know.
We'll probably try to, if it's
in the meantime, Lina, tell me, have you heard from Ganatra or
not yet. So I tried again, but he didn't reply this last email. I'll try again.
Okay, so
I'll try again over the weekend, and then if he doesn't,
tell him that his talk either will be in a week from now, or we'll finish seminar in April.
okay, yeah.
Actually, maybe we have already finished if Murad will not show up.
Yeah.
Okay.
No.
It's something.
If this, yeah, if it was just a, oh, I think it seems to be back. It was probably just maybe.
Currently, it's like 8 p.m. in Edinburgh. Okay, great. So yeah, it looks like.
Sorry, I was very reluctant whether I should still do this at the university or in my place in order to avoid potential problems. It seemed I'm sorry for that. So I probably took me a while.
Okay, but maybe you can kind of, that's a sign that you can squeeze your introduction, motivation and introduction. Yeah, okay, it's just a joke. Yeah, okay. Try to share a screen. Oh. Yes. Okay, great.
Wait, so what was the last thing you
you can start from here. I mean, it's some general words. So
okay.
Yeah.
Good. Okay, so let me move on. So just quickly recall. So mirror symmetry started from physics. So it's a statement that there are two physical string theories living in 10 dimensions. So when these are considered, these 10-dimensional spaces are considered as products of a real 6-dimensional complex 3-dimensional Calabi-Yau manifolds times Minkowskian R4. then it was observed that these lead to identical, what will be called four-dimensional n=2 theories. And actually, so the way these theories are formulated are in terms of what are called nonlinear sigma models, so maps from Riemann surfaces into the 10-dimensional space. And a reason mirror symmetry was very effective is that on the level of the isomorphism of the two-dimensional superconformal field theories underlying these nonlinear sigma models, there is a notion of deformation spaces. So there is a notion of moduli space already popping up here. And the moduli space here gets translated both into a notion of moduli space of the Calabi-Yau manifold, as well as a moduli space of the underlying four-dimensional theory. So there's many different perspectives leading to the same notion of moduli space, but it really parameterizes very different mathematical and physical objects. So in particular, the moduli space is involved for the Calabi-Yau threefolds. So on one side, that I'll call the B side, are the moduli spaces of complex structures. On the other side, it's the moduli space of complexified califorms, which is a bit more challenging to formulate mathematically. And the notion of mirror symmetry really caught a lot of attention because not only identifies the moduli spaces, so the Calabi-Yau manifolds over each point are distinct, but it identifies really complex vector bundles together with flat connections on both sides. So where on the complex structure side, the flat connection is the Gauss-Manin flat connection coming from a variation of hot structure problem on the middle dimensional cohomology, which are the fibers of this complex vector bundle. And on the A side, this flat connection is known as the quantum cohomology. So in particular, data of the flat connection or from the flat connections, a particular generating function can be obtained, and that's the prepotential or the genus 0 generating function of Gromov-Witten invariants, which in terms of some formal variables on the A side or local coordinates on the B side has a generic expansion of this way, where the Gromov-Witten invariants are the coefficients of the expansions in terms of the exponentiated variable. So next question is there an analogous thing? So these are genus 0 Gromov-Witten invariants, rational numbers. Is there an analogous generating function for higher genus Gromov-Witten invariants? And yes, if you just formally collect higher genus Gromov-Witten invariants in terms of higher genus generating functions, and then you can just introduce yet another formal variables where you sum over all genera, then what you get is known as the Gromov-Witten potential. And then the question is, okay, if the genus 0 is captured by a variation of hot structure and flat connections, how are the higher genera captured? And again, there is a physics answer to that, namely if you take the exponential of this Gromov-Witten potential, then this is something that you can obtain from what is called topological string theory. So topological string theory, for the purpose of the talk, will be the thing that associates to a Calabi-Yau manifold this particular generating series depending on a formal parameter lambda, as well as a set of local coordinates on the underlying moduli space, so both on the A side and on the B side. And again, these will be related by mirror symmetry. And in the rest of the talk, so we'll come back to this, formal generating function in terms of lambda, this parameter keeping track of the genus, is an asymptotic series. And the upshot is that on the B side, there is an understanding that this generating function of higher genus Gromov-Witten invariants, which is obtained from topological string theory, and topological string theory can be formulated as a flat section of a certain bundle with projectively flat connection. And this certain bundle is a bundle of Hilbert spaces that are obtained from a geometric quantization problem. And these flat connections, so this was recognized by Witten as being a geometric quantization problem, but the flat connection was a priori a set of differential equations relating higher genus topological strings to lower genera. So some recursive set of differential equations by Brzezinski, Chikoty, Aguri, and Buff. So let's go back to the Gromov-Witten potential, which is obtained from topological string theory. So generically, you can also separate this into two pieces. And so there's additional also genus 0 and genus 1 terms that I have not spelled out here. So one piece that is coming from constant maps and one piece that is coming from non-constant maps. For the piece that is not coming from non-constant maps, Gopal-Kumar and Vafa suggested the following reorganization of the Gromov-Witten invariants, where instead of having the asymptotic series in lambda, there's another expansion where lambda now appears in terms of this in this form in the exponential I lambda. So this is what's happening in this sign here. So, and these are the Gopal-Kumar Vafa invariants, so they're integer. I think that's been proven now by Parker and Yeoman. Okay, and so here you get to the point where the original Gromov-Witten theory was defined as an asymptotic series, but if you look at this expression, so assuming some convergence, this is an expression which has potentially meaning beyond an asymptotic series. Namely, this looks like potentially something that can be interpreted as a meromorphic function in lambda, and this is also something that I'll come back to in the talk. So the talk is about, okay, is there any meaningful complex holomorphic structure in lambda apart from just being a formal variable leading to an asymptotic series? And the answer is going to be yes. And this expression is going to be one of the examples of how this can be a meaningful function in lambda. Okay, so let's relate the mirror symmetry, which is sort of flat connections and matching differential equations on both sides. And now switch gears and state homological mirror symmetry as formulated by Kuntsevich. So this is saying, okay, the thing that you should match for a pair of Calabi-Yau manifolds are two categories. So the bounded derived category of Korean sheaves on one side and a derived Fukaya category on the other side. And here you may ask, okay, I was emphasizing the role of moduli spaces and the fact that you were studying families and there were flat connections. So what happened to the notion of families in this setup? And the answer is, again, input from physics, as far as I understand. Namely, you're not really, from the physics perspective, you're not really interested in the full categories, but just on some sub-categories which correspond to special physical objects, which are called BPS objects. So in a physical theories, BPS refers to a lower bound on the mass of a given object. It's Bogomolny, Prasad, and Sommerfeld. So for a given charge or a given element in some lattice, that is part of the definition of the theory, these BPS objects are the ones saturating a lower bound. So they're the lightest charged particles of a given theory. So this leads to a notion of a stability condition, which has been formulated by Douglas, Fjoll, and Römelsberger, and also then later by Douglas in more mathematical terms, and was abstracted further mathematically by Tom Bridgeland. And then the statement of mirror symmetry becomes that stable coherent sheaves should be matched with special Lagrangians. And both of these sides have innovative geometry interpretation in terms of Donaldson-Thomas invariants. And here, the interesting, very rich structure that comes with this is the fact that the stability, there is generically, so this is how the moduli space is coming in again as a space of stability conditions. And generically, objects that are stable somewhere or with respect to some stability condition do not remain stable all over this space, but generically the space is divided into chambers, and there's wall crossing structures as have been around in physics, studied by Chikoty, Vafa, Zyberg, and Witten, the NEF, and then a lot of excitement was triggered by Kuntsevich, Soberman, Joyce Song, etc. Okay, so now the question that poses itself, okay, in terms of generating functions, if there is a generating function of Donaldson-Thomas invariants on both sides of mirror symmetry, which translates into a physics generating function of BPS invariants, then what does this have to do with the generating function of Gromov-Witten invariants? And this is also not a new question. So that's been around for a long time. So there is work of Maulik, Nekrasov, Ogukov, and Pandey Panda stating that the two are equal for a set of Donaldson-Thomas invariants for a set of Calabi-Yau manifolds. And the equality of the two just involves a rewriting of the formal expansion parameter that I called lambda in terms of exponential of I lambda. So this is very much in the spirit of the Korkumar-Waffa resummation. The physics counterpart of this is known as the Oguri-Strominger-Waffa conjecture, relating topological string theory to BPS and generating function, which in that case is a black hole partition function. More recent work, so maybe in the last 5-6 years. So based on work of Gayoto Moore-Knightsky, studying these wall crossing structures, Tom Bridgent formulated Riemann-Hilbert problem, and he has shown that in certain cases this admits a solution, and in particular cases where the BPS structures or the Donaldson-Thomas invariants come from very simple Calabi-Yau manifolds. He has shown that this contains, or a solution of the Riemann-Hilbert problem coming from the wall crossing structure of Donaldson-Thomas invariants, contains as an asymptotic expansion the Gromov-Witten invariants of the same underlying geometry. So it's natural to ask whether given...
What precise statement, excuse me, Brad, because you...
Sorry?
What's a precise statement if you know, because BPS, it's the same BPS invariant, same as Donaldson-Thomas, they indeed give you the Riemann-Hilbert problem, which actually was formulated by Kontsevich and myself, and whatever Bridgeland did, it's kind of secondary thing, but this implication arrow, what's a precise statement?
Okay, so so you should invite Tom to give the talk about the precise statement. The precise statement that I have in mind is that the BPS or the Donaldson-Thomas problem, where this was stated the most precise that I know, is for the resolved conifold, is that the solution of the Riemann-Hilbert problem, there is a generating function that Tom called the tau function, which generates the torus coordinates, and the tau function itself has an asymptotic expansion, which gives
just for the resolved conifold. Yeah, it's just one example. Yeah, so that's
yes, exactly.
Okay. So then it's not a general statement. So then when you ask an opposite arrow, so about the opposite arrow, it's as general as this and the above one, or
so the precise statement for both arrows, as far as I can say now, is for the resolved conifold. What I'll be able to say, but this is also work in progress of mine, is that there is also a statement beyond the resolved conifold. So the resolved conifold is sort of a, in a precise way, a building block for Gromov-Witten theory more generally for Calabi-Yau manifolds. And this will lead also more
non-compact Calabi-Yau manifolds.
Sorry, what?
For non-compact Calabi-Yau manifolds, I don't think that you can say anything about compact.
So I can say something about the formal generating functions. So I can say something about the convergence because
for compact Calabi-Yau, there is absolutely no chance to have analytic wall crossing structure in the terminology of Maxim and myself because of the growth of DT invariants is like this OSV conjecture. It's more than exponential. So then I don't think that this arrow makes sense for compact Calabi-Yau. So that's And also it has nothing to do with Gayota-Morinetsky, which work only for some non-compact, like for those Calabi-Yau, which arise in geometric engineering of class S theories. So that's probably, it's kind of, what is written on this slide is a little bit more general than maybe much more general than people know. It's wishful thinking.
So what is precisely your complaint about the slide? So
It's not a complaint.
is a
It's
question.
not a complaint. It's a remark that for compact Calabi-Yau, I do not know. I do not know this arrow even from BPS to Z top. Maybe I'm wrong, but because the Riemann-Hilbert problem, it does not define the analytic wall-crossing structure because the growth of DT invariants is too large. It's super exponential. And therefore, you do not have any analytic function for compact Calabi-Yau. So that's my concern. And if you don't, then you cannot analytically continue.
Yes, but as far as I know, so in terms of if you're about precise statements, so I think what I think is that the expectation that the Riemann-Hilbert problem solution will also give this the same.
There are no, well, this I'm concerned because I don't think there are solutions to this Riemann-Hilbert problem. Because
yes, but that's even true for non-compact Calabi-Yau manifolds.
Huh? For compact
That's even true for non-compact Calabi-Yau manifolds.
Oh, no, for non-compact, that's fine. But for compact, I do not understand. Yeah. For
No,
non-compact,
but I'm not aware of any solution of non-compact Calabi-Yau where this.
yeah, resolve conifold, it's non-compact Calabi-Yau.
Yes, but that's the only example that I know, and this is what I mentioned.
Yeah. But I mean that for non-compact, you can kind of speculate that in general there is such relation. That's fine. But for compact, I think it's kind of a very wild conjecture that there is a relation. So I don't know. If it's true, then I would ask for explanations. I can believe for, say, for toric Calabi-Yau, this is true, that you can relate one thing to another one. But for non-compact, for compact, it's kind of, it looks a
So
bit.
I don't believe that I have made any general statements about compact Calabi-Yaus on this slide. So you asked me about how precise the statement is. So as far as I know, the full solution of the Riemann-Hilbert problem that it actually encodes Gromov-Witten invariants and work of Tom is explicit for the resolved conifold, but I think the expectation is, as you said, more general. But I'm not aware of a more general proof or,
maybe I misunderstood.
Okay, so the talk is about if there is any analytic structure in of topological string theory in lambda. So within topological string theory, this will be called non-perturbative completion, and that's been addressed in many different works. So exploiting many different relations of topological string theory to other interesting areas of mathematical physics, such that matrix models, Chern-Simons theory, spectral theory, superconformal theories, etc. But one thing that I've been thinking about is really, is there some intrinsic way of characterizing the lambda dependence of topological string theory, as was done for the moduli dependence. So the moduli dependence, the T dependence, is captured by some set of differential equations coming from flat connections. And that's work with Yau and J. Zhao from a long time ago. What we were able to show is that knowing some polynomial structure generically for topological strings on compact and non-compact Calabi-Yau manifolds, there is a piece of the full answer for which we were able to derive an Airy differential equation. So that's sort of path that I was taking, and I was trying to find a set of differential equations in general. And in this talk, I'll talk about a difference equation, but again, this is specific. So maybe, so this is very general. So this is for all Calabi-Yau manifolds in a particular limit. A difference equation, as far as I know, is just in one, and so not just one, but in a set of examples. But this is not a generic thing, but I also expect that there should be some structure there for compact and non-compact Calabi-Yau manifolds. But I don't have this, so maybe it will. Okay, so another intrinsic way of characterizing this is starting from the asymptotic series, saying, okay, there is the program of resurgence and Borel summation where you can treat asymptotic series, and also this has been done previously. So these are all works that in particular also addressed the result conifold, but also other non-compact Calabi-Yau manifolds. So in this talk, I'll be what is explicit, and what we formulated the theorems is the explicit expressions for Borel transforms, and then maybe I'll end with some speculations about how this generalizes. Okay, so the results are very explicit for a geometry known as the resolved conifold. So that's the conifold singularity in C4. And there's two ways of dealing with this singularity. One of them is a deformation, so replacing the zero with a non-zero complex parameter. And the other one is a small resolution, and that's replacing the origin here with a P1. And so I'll be talking about the small resolution, but for both cases, topological strings are explicitly known to all orders, and both cases can be treated using resurgence. But it's only this case that has a known Gromov-Witten theory, so that's what I'm going to focus on. So for the small resolution, the total space of the Calabi-Yau is the rank 2 bundle over P1, and that's known as the resolved conifold. So the local coordinate T on this space M that I was mentioning is the integral of the Kähler-form and some two form. It's called the B field that's making this parameter complex. And all genus Gromov-Witten invariants for this geometry, and also the all genus topological string theory was put forward by Kumar and Waffa, exploiting another duality with Trent-Simons theory, but this has also been proven to be the correct mathematical Gromov-Witten generating series by Faber and van der Eyck. So what's appearing here is a polylogarithm function defined in this way. And you can explicitly here see from knowing the growth of Bernoulli numbers that this is an asymptotic series in lambda. However, if you look at the Gopal-Kumar-Waffa resummation, so casting this asymptotic series in lambda into this form, do this for this example, then it leads to the following expression. So here there's really just one non-vanishing Gopal-Kumar-Waffa invariant, and that's the one at genus 0 and degree of the curve class on the P1 equal 1. So this is this expression. And this expression you can also think of as giving you a meromorphic function in lambda, which has infinitely many poles on the real axis. And what I'm going to answer in this talk is that this can actually be also thought of as a Borel resummation or as an analytic function behind the asymptotic expansion for a Gromov-Witten theory of this example. So since for this example, the all genus generating functions were known, and for a long time I was looking for differential equations in lambda, I was playing around with this example. And what I found, and actually repeating very similar arguments for another example of Iwaki, Koike, and Takei, is that this asymptotic series satisfies the following very simple finite difference equation. So if you shift the local coordinate on the moduli space by amounts of lambda divided by 2 pi, then what you get on the right-hand side, so this is essentially just a log of 1 minus q. And one advantage of having this equation is that you can relate it to the integrable hierarchies. I will not be talking about this. But then another thing you can ask, okay, what good is an equation for if you already know what the solution is? So, and then the answer to that is, okay, if a solution is the asymptotic series, then maybe in parallel to cases of differential equations, you can hope that some analytic function, also lambda, would be also a solution of this equation. And this turned out to be the case. So not only the asymptotic expansion corresponding to Gromov-Witten theory of the resolved conifold is a solution of this equation, but there is also an analytic function. So this is one particular representation of the function, but it's really a function that you can write down everywhere. It's related to what's called the triple sign function. So also this is a solution of this difference equation. And in fact, it also relates to Bridgen's tau function, which solves the Riemann-Hilbert problem in this case. So then the question is this sort of the unique analytic function that should replace the asymptotic function at the asymptotic expansion corresponding to Gromov-Witten theory. So what I did is also looking at if you cast this analytic function in the Gopa-Kumar-Vafa form, then what you find that it has the Gopa-Kumar-Vafa form, but it also has infinitely many correction terms, and all of these are exponentially suppressed. So they are all exponentials of something divided by lambda. And this, in fact, also matched some expectations based on the topological string spectral theory correspondence, and also some earlier computations of Hatsuda and Okuyan. So talking to colleagues in Hamburg about this, in particular, Jörg Teschner had the expectation that there shouldn't be a unique function, but rather it should be infinitely many. So we decided to revisit the problem and really using techniques of resurgence. So maybe let me just recap this in one slide and one example. So if you have an asymptotic series, so let's say it's that's a power series near 0, but it's asymptotic, meaning it doesn't converge. And a typical reason for a series to be asymptotic is the growth of the nth coefficient as n factorial. Then what you can look at is the Borel transform. So that's a new series built out of the old series where you just by hand take the old coefficient and divide by the factorial. So the shift by 1 here is just a convention. And then you introduce a new variable. And then you're guaranteed, if the starting function is of a certain class, that this Borel transform in terms of the new variable has a finite radius of convergence. So it corresponds to some holomorphic function, at least on some disk. Then the next thing you want to do is ask yourself whether you're able to analytically continue this function in the new variable xi to at least, to have some ray in the complex xi plane. And you want this in order to define the Borel sum. And this is really just exploiting the term by term, undoing this by hand, dividing by the factorial can be undone by the Laplace transform. So in general, the Laplace transform would be along the real axis, but here I'm allowing generic rho. So rho will be just a half ray in the complex plane. So let's look at an example. So a reason for a series to be asymptotic if the nth coefficient grows factorially. So here, let's just say that the nth coefficient is n minus 1 factorial. Then the Borel transform is a very simple power series that you can recognize from this expression here as the geometric series. So from this expression, the power series has finite radius of convergence, namely 1. But we know the expression for the geometric series, so that's also the expansion of 1 over 1 minus xi. And this is giving us the analytic continuation. So this expression is already the analytic continuation of the Borel transform to the Borel plane, and it's an explicit meromorphic function. So then the Borel sum is given by the Laplace transform. But in order for this to make sense, the rho needs to be a ray which avoids the singularity. So in particular, it cannot be the real positive real axis. So then the question is, okay, if you have to avoid the singularities and just pick some ray, then what's the relation between different choices that you can make? And this is something that you can address. So in this simple example, you can say, okay, you can avoid the pole of this meromorphic function at 1 by just going either above the pole or below the pole. And then the difference of these two is just a simple residue computation. And you see that the difference is something exponential in 1 over the original variable. So that's something that doesn't appear in the power series expansion. And that will be called the Stokes factor. So what I showed you explicitly in this very simple example is something that we did for the resolved conifold. So also there we had the explicit all orders series in lambda. So we can just take this all order series, divide the g's coefficient by g factorial. And what we proved is that the Borel transform for the resolved conifold is given by this expression. And we heavily used techniques that were developed by Garofalidis and Kashayev, looking at the resurgence of the quantum dilogarithm. So essentially the resolved conifold is a lot of very similar structure to that. So what you see in particular from this expression is that it has double and simple poles whenever this expression here is 1. And this is happening at infinitely many points in the Borel plane. So both k and m are integers. So I should have, so m is an integer, but it cannot be 0, but k can be any integer. So if you want to draw in the Borel plane where these singularities are, and then you find some diagram like this. So this is just fixing some particular value for t. So we find that there's infinitely many singularities along infinitely many rays. So each ray you can label by an integer k. And on the ray, you'll have infinitely many singularities labeled by another integer m. So now the task is wherever there is no singularities, you can just take some ray rho and then define the Borel sum corresponding to this Gromov-Witten problem along this ray. And then the next question is, what is the difference between two different Borel sums?
Sorry, may I interrupt you? So is it a picture in the Borel plane or it's...
Yes, that's a picture in the Borel plane. As you can see here, there is real part of Xi and imaginary part of Xi.
I think that the kind of terminology then a little bit incorrect, because Stokes rays, it's not what happened in the Borel plane. Well, I think there are different schools, but the infinitely many singularities for the Borel transform, it's sort of for people in the audience who know the Landau-Ginzburg story, it's sort of analog of the infinitely many critical values of the Landau-Ginzburg potential.
Yeah, sorry. So the
Stokes
complaint about the
rays,
terminology is Stokes rays.
and then the connection has only regular singularity. So there are no Stokes rays for regular connections. But if you do the Fourier transform, then you will have irregular singularity at one point, and then you can speak about Stokes rays. So then the terminology, it's kind of a little bit inconsistent with what mathematicians say.
Okay, I apologize for that. So what is meant is precisely what is written there. So it's infinite many rays of singularities in the Borel plane. Okay, so then you can also label, so rho k plus 1 or rho k in general would be any ray between rays of singularities labeled by that I called LK and LK plus 1. And then you can compute the difference of Borel sums along two different rays. And that's going to be a sum of infinitely many residues, which, however, summed up had this nice expression in terms of the logarithm. So, and in particular, what you recover is that f rho 0. So let's go back. So that will be, for instance, rho 0 could be anything between 0 and -1 in this terminology. So it can be on the real axis. So f rho 0 is the original. So the one particular resummation of the original asymptotic series and these infinitely many additional factors. And from this and from knowing the infinitely many jumps, what you can do is just compute what you would assign, what kind of Borel sum you would assign to the imaginary axis, which is not something that you can do straight away because the singularities are dense near that ray. However, what you can do really precisely is compute all the Stokes jumps of the different Borel sums up to the negative imaginary axis and the positive imaginary axis. And what you find is that precisely this whole expression here is the sum, or it's negative of the sum of all these Stokes jumps, leading to the conclusion that along the imaginary axis, you can formally say what f rho infinity is. And that would be this original just Kupa-Kumar-Waffa expression. So in that sense, you can say Kupa-Kumar-Waffa expression is a limiting Borel sum in this case. Okay, so here again, Jan's complaint was about labeling this Stokes ray. So what I mean is each ray of singularities is labeled by the charge of a BPS state or some element in the lattice to which there could correspond a stable coherent sheaf or Donaldson-Thomas invariant. And it turns out that all these, or the jump of the Borel sums of the associated to the Gromov-Witten invariants are given by some prefactor, and this prefactor is a BPS invariant, which is related to a Donaldson-Thomas invariant. And most of these for this example are 1. So all of these integers are 1, except the one, the limiting one. So that's -2, and that was a pain to really obtain, but this is really something that we could make precise. So one way of understanding this is that the Borel sums give you some piecewise analytic function. Another way is to say, okay, this is or exponentials of this function. The partition functions are sections of a line bundle, and each one of these choices corresponds to a different section.
Sorry, what is the rho or p? I don't know the notation. I'm confused with the notation. No, it's rho. What is rho? F rho, index rho. I'm trying.
Yeah, sorry. So that's yeah. So I introduced this here. So phi is the original asymptotic series. So f, the original one will be the Gromov-Witten asymptotic series. F rho is the Borel sum of the Borel transform along the ray rho.
Rho is the ray. So
Yes.
okay. Okay.
Okay, so maybe so this is something speculative. So well, the results are not speculative, but their meaning. So once you have any of these f rows, so you get analytic functions that are valid at least in a half plane. So with these, what you can do is also expand in the inverse. So instead of having lambda small, what you can do is introduce a dual, so 1 over lambda, and then look at the expansion in 1 over lambda. And the natural set of variables that you would have is that the set of variables t you should also replace by t over lambda. And then the surprise is that this whole problem also has asymptotic expansions in the inverse variable. And there again, you can look at the resurgence, you can look at the Borel transforms, you get some interesting BPS invariants or DT type invariants. And also for there, so this terminology is again the difference of the Borel transforms of the asymptotic, the difference of the Borel sums corresponding to the asymptotic expansions in 1 over lambda, so that's the lambda dual, can again be given in some closed forms. And also these have connection to DT invariants that's related to what are called non-commutative DT invariants studied by Sandro and others.
How is it related?
Yes.
How is it related to this clever chamber? I kind of object the term non-commutative DT invariants because it's all DT invariants. It just counters.
Okay, but again, this is an objection that you should
No,
mention.
it's not really a
Mention.
serious objection, but how this, whatever, you have some formal series which comes from Gromov-Witten theory, and then you do Borel transform, you look for jumps and blah, blah, blah. And so you recover DT invariants for this connection or alien derivatives, whatever formula. But what you said, this problem is related to the non-commutative DT invariants. What do you mean?
Yes, so what we made precise is that the product of all Stokes jumps of the Borel problem corresponding to the dual expansion, this precisely gives the what Balázs calls the non-commutative DT generating function.
And again, it's still a resolved conifold. Yeah, we are still.
Yes.
Yeah. Okay. Good.
Yes, but now we have the resolved so part of the data of the resolved conifold is really just from Gromov-Witten theory, just the asymptotic expansion in lambda, and now you're able to asymptotically expand in 1 over lambda because you have access to the analytic structure behind this, having the explicit.
Yeah, but how to think about that? You see, in this DT story, you have this chamber structure. Some of them quiver, some of them geometric, blah, blah, blah. You have infinitely many walls. All right. Now, on the Gromov-Witten story, you have this formal expansion. You do Borel transform, and you have some infinitely many singularities. And so how these two pictures, is there a kind of, is it infinitesimal statement that you should look for jumps at these critical values, or you can connect? I mean,
I don't understand what you mean by infinitesimal statement.
Because this delta k, it's infinitesimal. You just go.
No, sorry. So
go above.
That's So that's a finite.
Yeah.
There's nothing infinitesimal about this.
No, it's infinitesimal in the sense that no, hold on. This is not. This
you
is
can
not.
take any two rows in
Yes.
and compute the difference of the Borel sums of any two rows that avoid the singularity.
Okay.
So you can also compute the difference between a row
delta k. I see. So okay, so I was confused with the notation. So delta k is the difference of the Borel sums of two different rays. It's not a jump like people in resurgence theory says. It's not a jump when you go above a fixed singularity and below. Yeah. Delta k. It's a question about.
Well, in some sense it is, but you can go above and below wherever you want. And particularly, you can also just take any two rays that avoid singularities and compute the difference of the Borel sums corresponding to the.
Let's go back, because you just kind of too many notation. There is some rule that no more than 6 notation in a given talk. So the jumps, I go back to your slide, to your page 30, the jumps encode the DT invariant associated to gamma. Now, let's see. So rho is a ray, yeah, and lambda t, it's some parameters coming from this Gromov-Witten generating series. Now, delta L of gamma applied, probably I kind of was too sleepy. What means delta L of gamma applied to F rho? Where is it? What's the
So
definition?
this is really just so what I have here. So it's really just the difference of F rho k plus 1 and F rho k. So if these are, so if rho k plus 1 and rho k are just avoiding the ray of singularities Lk, then this is what I meant by delta delta k. But it's really just
but in general, I see on your page 30, I see some formula for delta L gamma applied to F rho.
Yes, so this is a qualitative, because this is a talk and I want to transport an idea. So this is a qualitative statement. The precise statements you can all find in the paper, and this is the precise statements are precisely of this type here. So here you have the DT invariant corresponding to the array of singularities that I called LK previously.
Okay, all right. Thank you.
Okay, so I had started out with discussing a difference equation that I'd obtained more or less by analogy, by trying a lot, and by luck. And there was some inhomogeneous piece of this difference equation. What we found, so that's in joint work with Lotte Hollands and Iván Tulli, where we looked at many different other aspects of resurgence, also some refined case. But in particular, what you'll find is, so this is not just for the 1NP, but also for the F rows in general, is that there will be a different difference equation, namely, as opposed to the original Gromov-Witten theory, which was, or Gromov-Witten asymptotic expansion, which was periodic in T. The Borel sums are no longer periodic, but they're not periodic in a very precise sense. Sorry, so this is this really translates into a statement. So the NP was one particular Borel sum along the real axis, but this also translates into a difference equation for all F rows. Is that the failure of periodicity is given by this, and this is precisely one of the Stokes factors that we found. So the picture that is emerging is that there is sort of two dual difference equations. One of them, so each one of them can be obtained from the asymptotic expansion, either in lambda or in 1 over lambda. And their inhomogeneous piece corresponds to the Stokes factors of the other of the Borel sum of the other problem. So this is also a bit dense, but yeah, so again, this is contents of the paper with Lotte. So there we were also able to interpret. So one of the questions that are still open is what is sort of mathematical origin of the finite difference equation. And many difference equations have been studied in this context, and they often stem from what are called quantum curves and quantizations of mirror curves. And indeed, this finite difference equation also has an interpretation as a quantization of a curve, but it's a curve in some auxiliary space associated to the moduli space. So some phase space associated to the moduli space, and there's a curve in there, and this can be interpreted as the difference equation. And this quantity which obeys this difference equation, so this is just the original Gromov-Witten generating function. And this quantity corresponds to what is called a Nekrasov-Shatashvili limit of topological string theory. But this is also something that relates via WKB to what is called quantum periods. And in fact, this finite difference equation can be interpreted as a quantum Picard-Fuchs equation, namely higher lambda corrections to just the ordinary Picard-Fuchs equation, which is a statement about the flat connection on the mirror side of mirror symmetry. Okay, so in view of time, and also because most of this is speculative and not precise enough for this audience, let me just mention that there's what I mentioned, and this is already contained in the papers, are just expansions in lambda and 1 over lambda. So one natural question is there some additional modular structure, or is there any nice geometric structure in lambda? And this is work in progress, so there's nothing precise that I can say on this slide. Is yes, there is a relation, but it's a relation to what's called an elliptic gamma function. And also, this is also in progress, namely sort of formal manipulations, how you can show that the Gromov-Witten generating function, at least as a formal power series on any Calabi-Yau manifold. So if you start with this expression and rewrite the Kuba-Waffa invariants in terms of other invariants that are called sheaf invariants. So I'm using terminology of Jacopo Stoppa, following work of Maulik and Toda. Then you can show that at least on the level of formal expansions, this Gromov-Witten theory for any Calabi-Yau manifold can be written as an infinite sum of the formal generating functions, which are the Gromov-Witten theory of the resolved conifold, but evaluated at different arguments. Okay, and then of course, all the previous complaints about convergence and so on in the case of compact geometries hold, but at least one interesting thing that you can say here is, okay, for this asymptotic series, so each term in this infinite sum, you know what an analytic structure behind this is. So for each term, you can replace this each term with a corresponding analytic structure. Of course, you need to know more about the omega beta ends in order to say something about the whole sum. But at least if you do this, there's something interesting popping up, namely that the corrections or the 1 over lambda pieces, so although sort of the asymptotic expansion contains information about all genus Gromov-Witten invariants, the corrections that you obtain from these manipulations are just genus 0. But this is pretty much a work in progress, so please, the precise statements will follow hopefully soon. So let me conclude here. So I was addressing, first of all, ways of tackling analytic structure in lambda, and I mentioned this can be addressed by differential or difference equations. So again, this is differential equations for some sector in generality, difference equations so far only for one particular example. And Borel summation can be used in order to get analytic structure in this formal parameter. And this relates Gromov-Witten invariants, at least to a subset of DT invariants, which appear as Stokes jumps of the Borel sums. Okay, so and as a further motivation, okay, there's this formal parameter wants to be understood in terms of some geometry, and there's some interesting modular structure behind this, and there's some interesting generalization. So sorry for going a few minutes over time. So let me stop here, and thank you for your attention.
Thank you very much. Are there any questions? I have a question. So suppose that I simply assume that this topological partition function for topological string theory is indeed a solution to the quantized spectral curve, and do just WKB analysis. Yeah, just
I never said it's a solution of the quantized spectral curve, so that's
you did not, but some other people did.
Yeah, but
So,
that's not true in general.
huh?
That's not true.
Well, no, it's not true in general, but sometimes it's true. And actually, I don't know for the resolved manifold whether it's true or not.
No, it's not true. So the spectral curve or the mirror curve is capturing something different.
I quantize. Yeah, I mean it's a very old idea, which I believe goes back to digraph. And
Yes,
maybe
so I think when they wrote the paper, the
Hollands.
expectation was that the quantization of the mirror curve will have to do something with the topological string.
Yeah,
And
it
that's
has something to do. Of course, there is some ambiguity because when you solve the homogeneous equation, you can multiply your solution, but
no, it's not an ambiguity. So that's the content of my paper with Lotte Hollands and Iván Tulli. So we explicitly do this for the resolved conic
yeah,
field.
but anyway, the statement is that you quantize the spectral curve, and so the partition function on some associated three-dimensional Calabi-Yau manifold is a solution to this quantum whatever differential.
Yes, but this is not the topological string partition function. So this is not true.
What
It's
is
not the topological string partition function. It's what has been understood now. So this is a different partition function associated to some.
you mean what partition function do you mean? I am telling about some conjecture which I can give you the references on.
I know the reference and it's not true. So I'm telling you it's not true. So the topological string theory, so if you define it as the generating series of Gromov-Witten invariants, it is not a solution of the mirror curve. However, there is a precise relation which we made precise in our paper. You can look at the quantization of the mirror curve, and this will lead to what I mentioned at the end. So this will lead to what is called the quantum periods. And this is related to another limit of what is now known as the refined topological string in the Nekrasov-Shatashvili limit. So the quantization of the spectral curves or the quantization of the mirror curves is another quantum mechanical problem, and that corresponds to the quantum mechanical problem considered by Nekrasov and Shatashvili. And so in our paper, we make the relation precise. So if you have the Gromov-Witten or the topological string, then in order to obtain the other one, so the other one are not the quantization of the spectral curve. So the quantization of the spectral curve will give you some wave function which still depends on the spectral curve. However, in WKB, what you can do is look at the Voros symbols. So you can look at the analogs of period integrals in all orders in your WKB parameter. And these Voros symbols will be related.
You see, Murad, you're speaking too fast. I mean, I'm very slow in understanding things, but what I'm saying is the following. You look for the quantized spectral curve, you do the WKB analysis with solution, no matter how you call it. Now, and then you study the resurgent properties of this solution. Yeah, so great. So, which means that you do Borel transform, and then you look, for example, for the singularity. Okay. Now, this singularity, there are periods, at least the first approximation, there are periods of the spectral curve, like integrals of the form PDQ over the first homology of the spectral curve. Great. All right. So what are these periods? So the basis in the space of first homology is formed by these BPS curves in terminology of Gayota-Muranetsky, which are, in fact, DT invariants for a certain three-dimensional Calabi-Yau.
Yes.
So they're BPS states. So that's what I was trying. You're saying it's not true, but nevertheless.
No. So what? Yeah. So there's.
This is a statement. No. But this is a statement of the type which you present because you relate the Borel transform of the Gromov-Witten generating function with the DT invariants. Yeah.
Yes.
So that's
Yes.
you recover them. Okay. What I'm saying that if you do a WKB analysis of the solution of the quantum differential equation, you do recover DT invariants.
Yes.
Okay, and so maybe let me ask you a question: what's the relation between these two pictures? It's
Yes,
not
and
about Nekrasov-Saakashvili, it's kind of mathematical question.
it is also mathematical. So mathematical, there's been work of Pierre Bousseau and collaborators trying to make Gromov-Witten sense out of the Nekrasov-Saakashvili limit. So it's just another generating function whose full enumerative content is still to be developed, but which doesn't mean that it's not mathematical. So I'm saying in the second paper, so the one with Lotte Hollands and Iván Tulli, we precisely looked at this question. So there is resurgence of Gromov-Witten theory, as I mentioned. And there is also the mirror, and the mirror has the mirror curve, and you can take the mirror curve as differential, so as a finite difference operator, and you can do the exact WKB of that. And the exact WKB of that will have very similar singularity structure to what I described for the Gromov-Witten theory. So out of that,
can I
in
then
a very precise sense. So this is
that your statement is some kind of.
You didn't let me finish my statement.
No. You said that generating function for Gromov-Witten, it has nothing to do with this double.
No, that's not true. So I didn't say that. So if you, I mean, it's recorded.
Okay. Sorry.
I didn't say that. So it is related, but it's so what you get from the quantization of the curve is not the generating function of Gromov-Witten, or it's not the topological string, but it's something that is related. And I also said previously, what is related is this partition function. So in physical terminology, in the Nekrasov-Saakashvili limit, or in terms of Gromov-Witten theory, that's Gromov-Witten theory that so at least in the example of local P2, that is known to be related to a log Gromov-Witten theory. So, and these two things are very related, but they're not the same thing. So it's important to distinguish. And what we did in our paper with Lotte is making the relations precise. And the relation is, again, that the topological string itself is a generating function for the quantum period. And this is, if you want, that's also the content of Tom Bridgen's work. Namely, there is a single tau function, or not a function, there's a single section, which generates the solutions of the Riemann-Hilbert problem. So the solutions of the Riemann-Hilbert problem would be obtained from this quantization of the mirror curve as the Voros symbols. So you have as many formal C star torus, quantum torus variables as the rank of your underlying lattice, but there's a single topological string partition function, but this is a generating function for all of these, and it generates all of these via one difference equation. So if you have the topological string, then you can generate, well, this is again, so we made this precise for the resolved conifold. In a more general case, it's the expectation, and it's an expectation that sort of matches with Tom Bridgen's work, that there will be a single function generating all the solutions of the Riemann-Hilbert problem. And so one thing is the Gromov-Witten, and sort of all the solutions of the Riemann-Hilbert problem correspond to the solutions of the exact WKB problem.
Okay, any more questions? Well, if there are no questions, so let's thank the speaker for the interesting talk. Thank you, Murad.
Thanks.
And this is it for today. Okay.